Let's start with a good problem. Not just any problem, the Mario problem. So here we go. Last week you sold some pipe to your best customer, Mario, who used the pipe to connect Peach's castle, so there we go, there's the castle, to Yoshi's island, over there. Now Peach's castle is located on the edge of a large lake. Here's the lake. And the island you get to by going 5 kilometers along the shoreline, then 6 kilometers into the lake. Now there were 2 types of pipes used, one that can run along the shore, and a sturdier, but of course more expensive version that can be used in the water. Now this week Mario's brother, Luigi, is coming to get some pipe for a different project. As you are preparing the bill, you realize you misplaced the cost of the pipe used in the water. But you do recall the following 2 things. Number 1, the cost of the pipe that runs on the shore is 100 gold coins per kilometer. And number 2, that the minimum cost for Mario's project happened when the pipe went along the shoreline exactly 5 kilometers, and the remainder went in the water in a straight line to the island. Okay, well that's interesting. So, if W is the number of gold coins per kilometer for pipe that can be used in the water, determine W and the total bill for Mario. There's a hint. Set up an optimization problem for the total cost of the piping in terms of X, the amount of pipe on the shoreline, and also involves W. So see the picture below. So we're going to do an optimization problem. Okay, so in particular we want to say we're trying to optimize cost. Now what's the clue that there's an optimization problem involved at all? Well, the key word here to indicate there's an optimization problem is the word minimum. So when you see the word minimum, that means there's an optimization that's happened. So we're trying to minimize something, in particular minimizing cost. So we know we should set up a cost function, and then we should minimize it. So here we go. Cost depends on how far the pipe went along the shoreline. So there's 2 pieces here. There's the shoreline, and the shoreline is pretty easy in terms of X. It's X itself. So this is how far we go. And what's the cost? Well, it's 100 gold coins per kilometer. And so the cost for the shoreline is 100x. Okay, well what about the water? Now the water, that's this length here. Now we don't actually know how much the water pipe costs, so we'll call it W, but we do know how far it went because we see it's part of a triangle. Not just any triangle, but the right kind of triangle. So what do we have? Well, this side has length 6. This side, it's not 5 and it's not x, but it is 5 minus x, the difference between the 2. So the cost for the water pipe will be W times the square root of that side squared. 6 squared, I'll write that as 36, plus this other side squared. 5 minus x squared. And so there we go. Our cost is what's going to happen when we add these 2 pieces together. All right. So now let's rewrite this in a calculus way. What's a calculus way? Well, the calculus way is, of course, to rewrite the square root using our to the 1/2 power notation. Okay, to the 1/2 power. Now, what do we know? Well, we're trying to optimize it, but in fact, we kind of know something really interesting. Now, W is a fixed number. We don't know what W it is, but we were told that the optimum happened at 5/2 kilometers. Now that tells us that we know when the optimum happened. So what we know is that x equals 5/2. Since that's an optimum, it has to happen at a critical point. So we know where a critical point is. So in particular, what kind of critical point could it be? Well, probably we'll take a look at the derivative, but it probably has something to do with the derivative, and my bet is right now, based on what the function looks like, it's going to be where the derivative is 0. So here it's a case where we actually know where the optimum happened. We just need to figure out how to use that information to extract other information. In this particular case, we're after what can we say about W. So we want to take C prime. So C prime of X, what does that turn out to be? Well, it's 100 plus W, bring down the half, 1/2, times 36 plus 5 minus X squared to the minus 1/2 times the derivative of the inside. Well, the derivative of 36 is 0. The derivative of 5 minus X squared is 2 times 5 minus X times -1. And there we go. There's the derivative. Now we can do some things really quick. We can say the 2 and the half cancel. That's nice. That might help us. And now we say, okay, plug in 5/2. So C prime of 5/2. Now if you notice, we can see right away 5/2 really isn't a problem. Because when you plug in 5/2 here, you're not going to get a 0 to the negative power, so life is good. So it has to be the case that the derivative at 5/2 is 0. So we're going to get 100, that's fine, plus W times something. Well, let's fill in this other stuff here. 5 minus 5/2 is 5/2. Then we're going to get -1. Now let's actually do a little work to the side here. So we're going to have, I want to simplify, what does that become? So it's 36 plus 5/2 squared. So that would be 36 plus 25 over 4, which if we get that, 36 times 4 is 144, plus 25 divided by 4, and that turns out to be 169 over 4. Okay, so the inside part is 169 over 4. Well, it turns out 169 is a perfect square. And the square root of 169 is 13. And 4, also perfect square. So the square root of that is 2. So the square root of 169 over 4 is 13/2. But remember that there's a negative. So it's going to flip it. So when you work that out, what you'll end up with is 2 over 13. Okay, so again, this part becomes 2 over 13. Now from here, again, we can get some cancellation. The 2's cancel. And we start saying, all right, this is equal to 0, because that was our basic assumption. And so if we move stuff around, we're going to get minus 5 divided by 13 times W plus 100. So let's make it plus 5, or 13 times W equals 100, because we'll move it across. Divide by 5, that would be 20. Then multiply by 13 allows us to conclude that W is equal to 260. And there we go. That's how much the pipe cost. It cost 260 gold coins per kilometer. Okay, so we've now found W. And now, what about the total bill? The total bill for Mario. Well, see, now that we have W, we can update our cost function. So our cost function is now 100x plus 260 times the square root of 36 plus 5 minus x squared. But we plug in 5/2. So we get that the cost for Mario is equal to 100 times 5/2 plus 260 times the square root of 36 plus 5/2 squared. Now the good news is that we can work with this. This is 250. And this part, we actually worked that out. That's 169 over 4 on the inside. And so the square root of that would be what? Well, it would be 13 over 2. So we get 250 plus, if I divide by 2, that's 130 times 13. Well, 130 times 13, think of that as 13 times 13, which is 169, times 10. So we get 250 plus 1690, which means if we add that all together, we get 1,940. And that is how many gold coins it cost Mario to install that pipe. Okay, cool. Well, that's fun. Nice, nice. Now, what are we doing today? Well, today we're going to continue working on optimization problems. And so this is the, here we go. This is the same as what we had last time. So no big idea. We want to find something that gives us the largest or smallest output. So what do? Well, we understand the problem. We say, okay, what's being optimized? What can vary? Look for relationships. Draw a picture and label. That often helps. Sometimes it doesn't have to, but it often does. Express what's being optimized as a function of one variable. So if we have several things involved, we can look for constraints that help us get it down to one variable. And then finally, we find and classify critical points and remember to check the boundary. Okay. Well, fine. That's it. That's it. So nothing really new. We're just going to do lots of practice because the more we practice, the better we're going to get. And we need to get really good so that we can pass all of our upcoming exams. So let's do a problem. Here we go. You are designing a container which contains a cylinder. It's a cylinder with no top. Okay, so let's see if we can sketch that. So it's a cylinder, and it's an open cylinder, so there's no top, but of course there is a bottom. So the material to construct the bottom cost thrice. Thrice is just a very fancy way of saying 3 times. 3 times as much as the material to construct the sides. And the cylinder must have a volume of 192 pi cubic inches. Determine the radius and height of the least expensive cylinder given these constraints. Well, let's talk about our constraint. The volume has to be 192 pi. So we know that for a cylinder, the volume is the circle that's on the bottom times the height of the cylinder. We're told that's equal to 192 pi. So we can cancel off the pi's, and that allows us to say r squared h has to equal 192. So that gives us a relationship between r and h, which can help us solve for one and get us down to a single variable. Now let's talk about our cost. We have the bottom, and here the area on the bottom would be pi r squared. And then we have the side. Now the side, how do you think about it? Well, you can think about it as if you pull out some industrial strength scissors, cut up the cylinder and laid it flat. And if you did that, if you were to lay the cylinder flat, you'd see a rectangle where the height is h, and then the length of this rectangle is the perimeter of the circle. So that would be the perimeter of a circle is 2 pi times the radius. So we have that our cost, our function, is equal to, well, it's the area of the sides. So let's do that, the sides, 2 pi RH. So this is the side. And then there's the bottom, pi r squared. There's the bottom. But remember, the bottom costs thrice as the sides. So we're going to put a factor of 3 there, because that is what's going to help us say that this bottom costs 3 times as much. Okay, so there's our basic cost function. Now, our challenge here is that we have this h. So we really have 2 things, r and h. So what we're going to do is, let's get rid of the h. So coming back up here, I can solve for h and say it's 192 divided by r squared. So now we're going to get cost only in terms of r. So it's going to become 2 pi r times 192 over r squared plus 3 pi r squared. And before we take a derivative, let's clean it up. 2 times 192 is 384 pi divided by r plus 3 pi r squared. So let's take our cost function. Now it's a function of a single variable. So we take our derivative. Well, I haven't used a lot of space over here, so let's go ahead and use it. So we're going to have the derivative here. Well, think of this as r to the negative 1. So the negative 1 comes down, so that's negative 384 pi. R to the negative 2, which we can write as over r squared. Plus, here the 2 comes down, we'll get 6 pi times r. And we're looking for the critical points. Well, what are the critical points? One could be r equals 0, but obviously if r equals 0, that's not going to work, because then our volume would be 0. R could be infinity, then our height would be 0, but that would be a really expensive thing, so it's not going to be that. So we're really looking for, okay, where do we have our derivative equal to 0? Well, we can rearrange that. That tells us that 6 pi r has to equal 384 pi over r squared. Now at this point we can say, hey, the pi's, they don't matter. They go away. Well, that's good. And then something else we can do, we can move the r squared across, divide by 6. If we did that, we'd get r cubed is equal to 384 divided by 6. And we say, boy, I hope that's a nice number. It turns out it is. It's 64. Nice. That is nice. Okay, so then what is r? Well, the cubed root of 64 is 4. Okay, so now we know what r is. What about h? Well, to get h, we're going to take this r and plug it into that relationship, which gave h in terms of r. So we can now say h would be, well, 192 over 4 squared. So that's 192 divided by 16. Well, it turns out that if you take 192 and divide it by 16, well, you can think of it in your head, you can almost do this, because 16 times 10 would be 160. Then there's 32 left, which means I need 2 more 16, so that turns out to be 12, or a dozen. So our final answer, well, our radius r will be 4, and our height will be 12. And if we want it to be units, well, we can figure it out, because it was told that we were having, our measurement was in inches. So r equals 4 inches, and h equals 12 inches. And we're done. That's the answer. Cool. Nice. All right. Good. Well, that was a fun one. All right. What's the next one? Well, the next one, we are going to find the area of the largest rectangle with sides parallel to the x-axis and y-axis, with one corner at 0, 0, and the opposite corner on the curve y equals 6 over x squared plus 2x plus 9. Oh, well, that's interesting. That shouldn't be too bad. I mean, we have what? We have this curve. It's doing something. I don't know what it's doing. We know it's always going to be positive. In fact, you can see in the denominator, if you were to look at this a little bit closer, which I don't know if we really need to, but if we were, another way to write this is x squared plus 2x plus 1 plus 8. You're probably thinking, yes, it turns out 9 is 1 plus 8. But the reason that we can write it this way and be nice is x squared plus 2x plus 1. What is that? Well, it's a perfect square. So we say, oh, nice. So in some sense, what we can see here is it kind of has symmetry about x equals -1. It looks like it somewhat peaks at -1, and then it's going to go down. And notice I never divide by 0, so it doesn't blow up. And as I let x get big, I get close to 0 again. So there's my picture. So I'm going to start at the origin, and I'm going to go to some point. I'm going to make a little box. there's my box. And I say, okay, well, what's the area? Well, the area of my box is going to be, simply, it's going to be x, which is this length here, and then I'm going to have my f of x. So 6 over x squared plus 2x plus 9. So, there's our function. That's what we have to optimize. All right, so I can write that again as a single function. I'll just clean up a little tiny bit, not much. 6x over x squared plus 2x plus 9. Take the derivative, and what do we get? Well, quotient rule, we're going to take the bottom times the root of the top minus the top, which is just 6, times the root of the bottom, 2x plus 2, all over the bottom term squared. And if we multiply this out, what do we get? Well, we're going to get 6x squared plus 12x plus 18 minus 12x minus 12 all over x squared plus 2x plus 9. Whoops, and we forgot to square the denominator. But now we'll remember. Good. Good. The 12x's cancel, which is nice. And what do we end up with? Well, we seem, we are coming up with 6x squared plus 6 over x squared plus 2x plus 9 squared. All right. Well, this tells me I seem to have made a mistake because this is never 0 and it's never undefined. Well, let's double check our work. Come back up here. We're taking the bottom times the root of the top minus the top. Ah, there should have been an x here. Oh my gosh. Oh my gosh. Okay, well, never too late to correct yourself. I forgot there was an x. I thought there wasn't. Okay, well, that's good. So what do we really have? 6x squared plus 12x plus, and I guess this is actually 9 times 6. It wasn't 18. That's another mistake. Well, that's good. As we fix one mistake, we get to fix another for free. And then we're going to subtract, 12x squared plus 12x. And again, we're going to subtract that whole thing. And now, what do we have? Well, we can see that the 12x's still cancel. That's all right. The important thing is we're going to get something that actually we can work with. So what do we get? We get 6x squared minus 12x squared. That's minus 6x squared plus 54 divided by x squared plus 2x plus 9 squared. Okay. Now, let's think about what's true about a prime. Well, it's never undefined because the denominator is okay. That's something that we can work with. No problem. This problem really doesn't have any limits, per se. Now, one of the things we might say, well, maybe our area can get arbitrarily large if we let x go to infinity. But if we go back to our area function, if you let x go to infinity, what happens? Well, the thing is that the downstairs grows faster than the upstairs. So if you let x go to infinity, it goes to 0. Similar if you let x go to negative infinity. So the endpoints, which are plus minus infinity, those aren't the answer. So that leaves us with just one possibility, namely, what about if a prime of x is equal to 0? Well, when does that happen? The numerator has to be 0, so negative 6x squared plus 54 equals 0. And if you rewrite this, that becomes x squared is 54 divided by 6, which turns out to be 9. So you get x equals plus or minus 3. Now, well, what is it? Is it the plus 3 or is it the minus 3? We can actually figure this out, right? Because we can do 3 and negative 3. And if you do this, say you plug in something, say 0, you'll see that the derivative, a prime, is positive. Or if I plug in something bigger than 3, I don't know, like 100, I'll get that a prime is negative. And here a prime is negative. Now what do you notice? This says that, wait a second, 3 is at a max, but negative 3 is at a min. What? So 3? 3 is the right answer? Really? Really? Maybe. Or maybe not. Because we've got to be a little bit careful here, because let's actually go back and check again what's happening with our area function. The question is this the right formula? You might say, well, right, because we had to go, if this is our x, say this is x over here, then this would be our f of x. So length times height. But what if we'd gone over to this side? That looks pretty big. What about here? Well, now the problem is that our length is not x. So our real secret problem here is our formula for area was wrong. Should have been absolute value of x. But the good news is it doesn't really change anything. It just says, oh, wait a second, be careful of your sign. So we can do one of two things. We can say, okay, we can repeat the process, but if we repeat the process, the only thing that happens is we have a negative. And so what we'll see, again, is that negative 3 is a critical point. But the other thing we could say is just use our intuition and say, okay, well, look, if I want to maximize it, I'll just take a look and see when does the area get large in size, and regardless of sign. So I have really two candidates. I have at 3 or at negative 3. And now I just test. Well, if I plug in 3, what do I get? Well, plugging in 3, we would get, maybe it's easier to plug a 3 into here. I would get 6 over 4 squared, 6 times 3, 6 times 3, gotta keep track, over 4 squared plus 8. Well, that's 18. Divided that by 4 squared is 16 plus 24. 16 plus 8 is 24. So we get 18 over 24. Well, that's 3/4 equals 0.75. Where if we plugged in negative 3, well, if I plug it in just without paying attention to the absolute value, I get 6 times negative 3. Downstairs I'd have negative 3 plus 1 quantity squared. Well, that would be negative 2 squared plus 8. So I get negative 18. But downstairs now I have 4 plus 8, which is 12, which is negative 1.5, or negative 3/2. And we can see that the one that's actually larger in size is this at location at negative 3. So what's the largest area? So largest area is going to equal 3/2. And that's the answer. There you go. All right. So I rambled a lot there, and I feel like I didn't really answer what are you supposed to do in this situation. So I would say in this situation, the safest thing to do is just sort of use your intuition. Say, okay, if I have an absolute value, one option is do it twice. When x is positive, when x is negative, and then you'll find that you have two maxes. A max will happen at 3, and a max will happen at negative 3. And then you go through and work it out. The other thing is just say, look, I know I'm really looking for a number that's a measurement, so that's a positive number. I can't have negatives. So if I'm looking to maximize that number, I look at both the maxes and the mins and just see which one is larger in size. Either one will get you the correct answer. All right, well, let's try another one. So, you and your friends are going to Blips and Chits, and they're going to check out their newest game, Roy 2. Now, while you are there, you decide to spend 80 furbos to play your two favorite games. So the two favorite games you have, excuse me, are Meeseek's Mansion, which cost 1 floribel per game, and Chrombopulus Creed, which cost 2 floribels per game. Now the games are tied together so that the total time you would spend playing the games is 1 plus square root of k times m plus 4k. Determine how many times you should play each game to maximize the amount of time spent at blips and chits. Okay, well, let's think about what we have. Well, we know what we're trying to maximize. So we have this expression, 1 plus square root of k times m plus 4k. So this is what we want to maximize. Now our problem here is that the thing that we're trying to maximize has both k and m. And we can't optimize things with two different variables. I mean, not yet. In a year from now, sure, but not yet. So let's see, what else do we know? Well, we know we have 80 floribels. Okay, so that's a constraint. And Meeseek's Mansion cost 1 floribel, and Chrombopulus Creed cost 2 floribels. So we can say that the total number of floribels is equal to the number of times we play Meeseek's Mansion times 1, plus the number of times we play Chrombopulus Creed times 2. So we can use this to solve either m in terms of k or k in terms of m. Now, given that m only shows up once, it's probably easier to solve for m. So we say, aha, m is equal to 80 subtract 2k. So now we have that our function, let's write it as a function of just k that we're trying to optimize, is 1 plus square root of k times 80 minus 2k plus 4 times k. Now before we take any derivatives, let's multiply this out. So we're going to get 1 times 80 is 80. 1 times negative 2k. Square root of k times 80, that's 80 square root of k. And then square root of k times minus 2k. So that'll be minus 2k to the 3 halves. We have a plus 4k. You notice that the plus 4k and the minus 2k can go together. And so we end up with 80. And if we do this in powers that are sort of going down, so let's see, minus 2k to the 3 halves, that's the largest power. Plus 4k minus 2k is plus 2k. Then plus 80 times square root of k. Now we take our derivative. Our derivative as a function of k is equal to, well, derivative of 80, gone. Constant. And minus 2 times 3 halves times k to the 1 half. Then what comes next? Well, it'll be plus 2. And then finally, we have plus 80, and the derivative of k to the 1 half, which is 1 half k to the minus a half. So, let's see what we have. So clean that up. That's minus 3 times square root of k plus 2 plus 40 over square root of k. Now, at this point, it's not so obvious what to do, because it's not clear where the algebra goes. We certainly can see that when k equals 0, we're going to have an issue. Now, when k equals 0, that would say you should just play only Meeseek's Mansion, and we'll spend 80s. We'll go check to see what happens when k equals 0. But what can we do? Well, one thing we can do is we can say, well, let's factor out a factor of 1 over square root of k. And suppose we did that. And let's make this a plus. I'm going to factor a minus 1 over square root of k out. Now, the first term had a positive root k, but I factored 1 over root k out. So it'll become root k squared. I'm just going to write it like root k squared. Then plus 2, again, that didn't have a root k in it, plus 2 times root k, and then plus 40. But I did this again. I factored out a minus, so this should be a minus, and that should be a minus. And now, when we look at this, we say, well, that's interesting. That looks a lot more doable. That looks a lot more doable, especially if we remember that there was a 3 there. There we go. Yeah, now it definitely is a lot more doable. See, it may not look like it, but it really is a nice quadratic thing. So I can think of it as 3 times, I'll say, x squared minus 2x minus 40. So we have to see, does that factor? Well, it might. What are we trying to factor it as? Well, 3, there's not a lot of ways to do 3. So it has to be 3x and x. And now we think, okay, what about 40? Well, I have to have something that multiplies together to 40. What are some things that do that? Well, 40, we could have 10 and 4. That'd do it, right? And now, what's the key? Well, I have to be able to multiply one of them by 3 and get a difference of 2. So, of course, there are other things. There's 20 and 2. There's 40 and 1. There's 8 and 5. Oh, there's a ton of things that do it. But the reason I'm drawn to 10 and 4 is, notice if I multiply 3 times 4 gives me 12, and 1 times 10 gives me 10. And they differ by 2. So that says, hey, we should make one of these be 10 and 4. Now we just want to figure out the sign. Well, if I want to get a negative 2, so if I put a negative here, oh, I see I did that wrong. That's okay. That's why we're allowed to guess. 4 and 10. So if we put a negative on this one and a positive on this one, well, we get minus 12x plus 10x. It's minus 2x. And then, of course, minus 40. So it works out. So, what does that tell us? Well, it tells us that our derivative, picking back up again, is minus 1 over square root of k times 3 root k plus 10 times root k minus 4. Now, what could be wrong? Well, we have a couple of things. Okay, so where are the critical points? Well, one place we should think about is k equals 0. That's certainly a critical point, because that would be where the derivative is undefined. How about this term? Well, here, it won't actually be a critical point. Why not? Well, if 3 times root k plus 10 equals 0, that tells us that root k has to equal negative 10 thirds. I can't have the square root of a number be a negative 10 thirds. So that is out. Whatever comes out of the square root is positive. This one, though, that would say that root k has to equal 4. So the other possibility is that k is equal to 16. Now we should think about what happens. So suppose we have k equals 0. If k equals 0, again, we mentioned this before, you play Mises expansion all the time. On the other hand, if k equals 16, well, that says what? Well, we should play Mises expansion would be 80 minus 2 times 16. So that would be 80 subtract 32, which is 48. So, which one is the better deal? Should we just go ahead and throw our time and play Mises expansion nonstop? Well, probably not. Why not? Well, suppose we were to do this other alternative. What would we end up with? We should check. We don't need to check, but we should. 1 plus square root of 16, that's 5, times Mises expansion is 48, plus 4 times 16. Well, that, it's going to give us 240 minutes, plus an additional 84 minutes, not 84, 64, which gives us 304 minutes, which is a lot better than the 80 minutes we were going to get. So, here we go. We should play Crombopulus Creed, and of course the hard part about this is spelling Crombopulus, but the good news is we can cheat and copy. We should play that 16 times, and of course the Mises Mansion, we should be playing that 48 times. And there you go. That's how you can spend a lot of time at blips and chits. And that's the answer. All right, good. Be careful with your algebra. Always double check. In fact, if you can, triple check. Okay, find the point on y equals the curve square root of 2 over 2x squared, which is nearest to the point -6, comma, 4 root 2. Okay, well that's interesting. So what do we have? Well, we can say that we have is this parabola. That's a parabola that opens up. And now we have this point somewhere over here, -6, 4 root 2. And what we want to say is among all the points on the parabola, which one is closest to that point right there? So, well, how do you find that? We need to find a function to optimize. So what we can think of right now is that we have a point on a parabola is something that looks like the following. Is I have something that has the form x, and then I have y, where y happens to be square root of 2 over 2x squared. So what I want to do is, what's the distance between those two? And I want to figure out what's that function, and then I want to optimize that function. So the distance between 2 points is the following. The square root of, now we're going to take the difference between the x values. So I'll go from here to there. So x minus -6 become x plus 6 squared plus difference in the y values. Square root of 2 over 2 x squared minus 4 square root of 2 squared. And that's the distance function. So that's what we have to optimize. Now, one thing that we can look at and say, oh, this does not look fun, because that would involve optimizing something with the square root. Well, we have some good news. We can get rid of the square root. And here's how you do it. You don't write the square root. And now the square root is gone. You're probably thinking, wow, that's cool. Does that work all the time? Well, what's really going on here is when we write it this way, so here's our function of x, we're saying, look, if I want to optimize what's under the square root of something, I optimize what's the something. Because if I want the square root of something to be large, I make the something large. If I want the square root of something to be small, I make the something small. Because square root is what we call an increasing function. And therefore, to make it as small as possible, you make the inside as small as possible. Now, will it change the answer? No. Will it change how much work we do? Well, it certainly changes how much ink we need, because we're not going to have to write down so much. And we like it when we don't have to write down so much. So here's the function we're trying to optimize. And let's get to work. Now, I can't help but notice that on this second expression, let's see if we can do something about the square root of 2's. So this is x plus 6 quantity squared. I'm going to pull out a square root of 2 over 2. And if we do that, I'll get x squared from the first term. From the last term, I got the square root of 2. And what will I have left? Well, it'll be -8. Now, if we square that, well, we get x plus 6 squared. Square root of 2 over 2 squared would be 2/4, which is 1/2. So 1/2 x squared minus 8 squared. Okay, so now let's take the derivative, f prime of x. So we're going to get 2 times x plus 6 plus, here, 1/2 times 2, x squared minus 8 to the 1, times the derivative of the inside, because we got to do the chain rule. Now, the 1/2 and the 2 cancel. That's good news for us. We'll get 2x plus 12. And here we'll get x squared times 2x. That's 2x cubed. And then minus 8 times 2x is minus 16x. Okay. All right. Well, there you go. There you go. Well, let's see if we can't look at this for a second here. And everything has a 2. I might as well factor the 2 out. Then we get x cubed. And now what else do we have? There's no x squared terms. Okay, that's nice. The x terms, we had 2x minus 16x would be minus 10x. And so we pulled out the 5, pulled out a 2, which leaves us with 5x. And then, of course, we have plus 12, which makes us plus 6. Now, we start to look at this and say, did we get everything? Because it's good to know that you got everything. And make sure you didn't make any too serious algebra mistakes. But we can already spot one here, right? 2 minus 16 is not minus 10. It's minus 14. So this should have actually been a minus 7. Okay, good. Now, x cubed minus 7x plus 6. How can we do that? Well, you always try for some simple things. Well, we know 0 is not a root because we have the 6. How about other numbers? How about 1? Well, you get 1 minus 7 plus 6. Well, that's 0. So that tells us that 1 is a root, which is good. Well, why is that good? Well, that tells us that this becomes 2 times x minus 1 times something. Now, how can we figure out what the something is? Well, it's going to be a quadratic. So the first term we say, okay, I need to end up with an x cubed. I have an x. X times what gives x cubed? The answer is x squared. The last term comes saying, well, look, I need to get a 6. Negative 1 times what gives me 6? The answer is minus 6. The middle term, well, you can reason about it for a few minutes. And here's sort of like one argument to say, well, notice that there's no x squared. This right here will give me a minus x squared. So whatever comes here has to cancel with a minus x squared. So x times what will cancel with a minus x squared, and the answer is plus x. Now, if you don't like what we just did, you don't have to do it. You can always do the following, which is long division. X minus 1, x cubed plus 0x squared minus 7x plus 6. So x times what gives me x cubed? The answer is x squared. So x cubed minus x squared. And if I subtract, I'll get x squared minus 7x plus 6. X times what gives me x squared? The answer is x. So plus x. So then I'll have x squared minus x. Subtract. X squareds cancel. This will become minus 6x plus 6. X times what gives me minus 6x? And the answer is minus 6. Now we become minus 6x plus 6. And now we get a remainder of 0, which is good. And you'll see we got the same thing. So you can either reason it or you can do long division. Now, can you go any further? Well, I think we can. So let's see. X squared plus x minus 6. Well, that would be x. I need two things that multiply to negative 6, but add to positive 1. And I think plus 3 and minus 2 do that. Certainly 3 times negative 2 is negative 6. Plus 3x and minus 2x leaves us with x. So, what do we see? Well, the critical points, we have a bunch of them. We have one at 1, at negative 3, and at positive 2. Let's think about what's true about these critical points. So suppose we write these critical points down, negative 3, positive 1, and say 2, and we can say what's true about our sign. Well, for instance, suppose we take the 0, plug it in. Plug in 0, we're going to see positive, negative, positive, negative. It says f prime is positive. If you plug in something between 1 and 2, say 3/2, positive, positive, negative. So f prime is negative. Plug in something bigger than 2, say 100, positive, positive, positive. So we're increasing, plug in something really, say negative 100, negative, negative, negative. So what do we see? We're going down, then up. Here we're going up, then down. And here we're going down, then back up. So 2 is a min. 1 is also, negative 3 is also a min, and 1 is a max. So certainly, among these 3 candidates, it's not 1. Okay, so what is it? Is it negative 3 or is it 2? And so here would be a time when we could either say, well, we plug both negative 3 and 2 in and see what happens, or we say, look at the picture. Look at it. Does it make sense to say that the nearest point is here, or that I should go all the way across? See, if I go all the way across, I'm going to have to cross the parabola at some point. That's going to be near. So I can't go all the way. 2 won't be the minimum, because I can always do better. So therefore, the min, by reasoning, is at x equals negative 3. Okay, so if that's where the min happens, what's the point? Because remember, we got to answer the question that was asked. In this case, it was, what's the point? So the nearest point would be negative 3, comma, square root of 2 over 2 times negative 3 squared. Or, if we clean up just a little bit, negative 3, 9/2 square root of 2. And that is the point on the parabola closest to the point that was given to us. Okay, well, with all these warm-ups done, and hopefully by now we've gotten all our algebra mistakes out of our system, one more example. Determine the value of b, positive value of b. I want b greater than 0, so that the maximum area of the triangle whose sides are formed from the tangent line to y equals e to the negative bx at x equals a for some a greater than 0, the x-axis and the y-axis is 1. Now, I think the first reaction is, what? Okay, so let's sort of try to draw a picture and see if we can get some idea about what's going on. So e to the negative bx always has more or less the same form. It's coming down and it's going to have this exponential decay. So I have this thing going on. And it says you're taking the tangent line at some point A, and now when you take the tangent line here, what you end up with is you end up with the following. It's going to be a straight line that goes something like that. And now I form a triangle. Part of my triangle is the x-axis, part of it is the y-axis, and of course the rest of it is the tangent line. And I can say, okay, I want the area of this triangle to be maximized. So let's talk about how can I maximize this area. Well, for one thing we should ask, does it make sense to talk about can it be maximized? Well, the answer is as I move my tangent line, or rather as I change A, I do change the shape of the triangle. So when I change something, it makes sense to ask, when is it as large as possible? So suppose I wanted to go through it and figure out, when do I maximize this area? So here we go. This is the curve y is e to the minus bx. So what I'm going to do is I'm going to focus on finding this tangent line. So if I want the tangent line, what do I need? Well, I need to know the value of the point. So the x-coordinate is at a, the y-coordinate is at e to negative b times a. So there's the point. The slope, well, for that you'd use the derivative. Now what is that? Well, negative b e to the minus bx. So the slope would be minus b e to the minus b times a. Now, I have both my point and my slope. So, what's my tangent line? Well, y minus my y-coordinate is equal to my slope times x minus my x-coordinate. Good. So there's our tangent line. So now we found that line there. Well, what do we need? Well, we want a triangle. We've figured out this line, so we need to know the base and the height. So in particular, we want to figure out the x-intercept, and we want to figure out the y-intercept. Now, how do we figure those out? Well, the x-intercept, that's when we hit the x-axis. What's true about the x-axis? When I hit the x-axis, I have to be the case that y equals 0, because that's where I'm on the x-axis. So if you set y equal to 0, we can solve for x. So you get minus e to the minus ba is equal to minus b e to the minus ba times x minus a. Well, I can do a couple of things. I can get rid of the minus, and I can even divide by e to the minus ba, because that's not going to be 0. So that becomes 1 over b, because I can divide now by b, is equal to x minus a, or I can say that x is equal to a plus 1 over b. So that tells us that this point right here is at a plus 1 over b. All right, cool. Now, how about that other intercept, the y-intercept? Well, that would happen when x equals 0. So, what does that become? Well, it becomes y minus e to the minus ba is equal to minus b e to the minus ba times 0 minus a, which is negative a. So what I can do is I can say that y, well, here, minus b times minus a is plus ab, and then there's going to be one more from that side. So I write it as ab plus 1 times e to the minus b times a. So this point up here is ab plus 1 times e to the minus b times a. So that's my y-intercept. And therefore, if you give me a, I can tell you where my intercepts are at. All right. Well, now what? The next thing is to say, well, what's the area of the triangle? Because we're after trying to maximize the area of the triangle. So, we can say that our area is equal to 1/2 the base, which is this value, a plus 1 over b, times the height, which is this value, ab plus 1 times e to the minus ba. All right, so that's our area for any choice of a and any choice of b. Now here's what we're going to do. For right now, I want to hold b as a fixed term. So fix b. So I'm going to think of b as a constant. So for the next couple of minutes, every time we see that b, we're going to think of it as a constant. Because we want to maximize the area for a particular choice of b and say, how much area can we get out for some b? And so we're going to fix b, and we're going to figure out what that answer is. And then once we have that, then we're going to go and talk about what b should be. So right now, we're thinking of our area as a function just of a. So if our function is just a function only of a, well, then what we can do is we can take a derivative. Okay, so what's our derivative of area? So a prime, again, think of it as a function of a. So we actually have a bunch of terms. So because a shows up 3 times, we can do sort of our triple product rule. So it's 1/2 times the derivative of the first with respect to a is 1. So 1/2 times 1 times ab plus 1 times e to the minus ba. Then go to our next thing. So plus a half, the a plus 1 over b, times the derivative of the middle term with respect to a, which is b, times e to the minus ba, plus 1 half, the first two terms, and then finally the derivative of e to the minus ba with respect to a is e to the minus ba times negative b. So there it is. Now, let's factor out what they have in common, which is that e to the negative ba and, of course, the half. And let's see what's left. Now, from the first term, what's left is a times b plus 1. From the second term, we get a plus 1 over b times b, which is a times b plus 1, because you can multiply the b through. Well, that's kind of convenient. Now, from the last term, what do we have? Well, we have this minus b here, and if we multiply that through, say I multiply into here, well, I'll have minus, I'll write it as ab plus 1. So I can multiply the b through there, and then another ab plus 1. All right, so far so good? Are you hanging in there? Don't worry, we're almost there. We're almost there. I promise. We're really close. We're really close. So this becomes e to the minus ba over 2. And now you can do one of two things. Let's talk about sort of the simplest thing, which is to say the following. All these terms look like ab plus 1s. So what if we call ab plus 1? For a moment, we'll call it some other symbol, something we haven't used yet. Let's call it, I don't know, capital D. Then we have a 2 times a capital D minus a capital D squared. Right? Capital D plus capital D minus capital D times capital D. So if we did that, what would we end up with? Well, we would end up with the following. E to the minus ba over 2. And now I can pull out a d. And then what will be left will be 2 minus d. So that's e to the minus ba over 2. Remember, that's ab plus 1. And then 2 minus that, well, that'll be 2 minus ab plus 1. That's 2. It'll be negative ab plus 1. That's what it'll turn out to be. All right. So, where are our critical points? Well, we ask which parts can equal 0. Well, let's go through them one by one. Can this part equal 0? The answer is no. E to something can never equal 0. How about ab plus 1? Can this ever equal 0? And the answer is no. You might say, wait, hold on. Why not? Because a has to be greater than 0 and b has to be greater than 0. So a times b is definitely greater than 0. ab plus 1 can't. Well, that means, lo and behold, that is the only place where we can have a critical point. So we have to have a times b equals 1, which tells us that, remember, we're solving for a, that our critical point happens when a is 1 over b. All right, cool. Now, is that the maximum area? The answer is no, it's not even an area, but it tells us where to look. So now we know that our area is going to be maximized at 1 over b. So plug 1 over b into our area. So we're going to get 1/2 times 1 over b plus 1 over b. And now a is 1 over b, so 1 over b times b is 1 plus 1. So we're going to get 1 plus 1. And we're going to get e. And here, again, a times b equals 1. e to the minus 1. So 1/2, 1 plus 1 is 2, half times 2 is 1. So we're going to get 2 upstairs, because we get 1 over b, plus 1 over b is 2 over b. And now this e to the minus 1 is really 1 over b, so we get 2 over b times e. So if you set b, so for a fixed b, this is the maximal area. Well, what are we trying to do? We want the maximum area to be 1. See, the maximum area, and then there's this long, brief statement of maximum area is 1. So we want this maximum area had better be equal to 1. Well, flip both sides. b times e over 2 had better equal 1, which gives us our final answer that b had best be 2 divided by e. And that is the one for that particular choice of b. When we maximize the area that we can get in this fashion, the maximum will be 1. That's it. Wow. Amazing. Amazing. Beautiful, beautiful problem. We would be lucky to have all our problems work out so nicely. Of course, in math, we're often lucky. All right. That's it for today. Done.